In this video, I will demonstrate how to perform a one-sample z-test. So in the case of these particular tests, what we're trying to do is compare a sample of data we've collected and compare that mean score for that particular sample to a known score, typically a population mean, to see if the sample we have collected is different from the population in general. So typically, we're going to need to know the population mean for whatever it is we're measuring. And then we take the data we have collected in our sample, and then we're going to compare those two to see if they're significantly different. So very often this is done to see if there's been some kind of there is a difference in a sample of people compared to the population. So perhaps in the example we're going to look at here, you know the population mean for score on a reading exam, and you want to compare your sample, perhaps students in your class, to see if they might differ from the population of all the other students that are out there, to see if your course or your class in which you're teaching reading might result in different reading scores compared to the population in general. So this is a fairly common situation in which we have population data that we want to compare a sample to. Many variables out there we don't have population data for, but if we do, and which is very often the case with standardized tests, we have a population mean we can compare our sample to see if our sample is somehow different. So the first step in doing this is make sure we have set ourselves up a null hypothesis. So the null hypothesis when we're doing any kind of hypothesis testing typically is that the sample will not be different from the population mean. In other words, there will be no difference between the two sets of scores. And remember, when we talk about differences, we're talking about relative differences. The actual samples might differ numerically. You might have a sample of 75 and a sample of 76. Now, those two scores are different numerically, but they might not be different in a statistical sense. In other words, are the differences we're seeing due to something explainable, or are they just due to chance? And so that's typically what we're using hypothesis testing to do, is to understand if differences I'm seeing in sets of scores are due to something that's explainable, either an intervention or some kind of a characteristic that would then explain that difference, as opposed to just the scores being different because of some kind of random event or something unexplainable. So in this case, we're looking at variable A, which is reading 1 score. So this is score on a standardized reading assessment. And we're going to compare the scores that we see here in our sample. We have 150 people that have taken this reading assessment. And we want to compare it to the known score within the population. So we want to see if our sample of people are different from the population. So we're going to assume that the scores in this reading 1 scale are normally distributed. That is a precondition for doing a one-sample z-test, is that the scores that are our outcome or dependent variable are normally distributed. And so the other assumption, the other precondition, is that we know the population mean that we want to compare to. So we know the population mean, and we'll talk about that in just a minute. And then we've already assessed the skewness of our scores here, and we determined that they are normally distributed based upon the skewness score. So we can move ahead with the analysis. So we're going to go to the analysis menu, and we're going to find z-tests, and we're going to choose the one sample z-test. Okay, now there's a couple things we need to do before we can run the actual test. And the first is we have to go to the options button. And this is where we set up the type of hypothesis test we're going to do. And in your readings, you've read about this idea of setting an alpha level to determine whether or not the differences we're seeing are true differences versus chance differences. And also the type of test as far as the number of tails. And so we typically test two-tailed because we don't necessarily know if the sample mean will be above the population mean or below the population mean. And so we need to test for both directions of possibilities. So we can determine if the sample is less than the population mean or is greater than the population mean. Is either one of those differences statistically significant? And so we typically are going to test two-tailed. We'll get into more detail as we get later in the course as how we choose one-tailed versus two-tailed. But for most cases, we're interested in doing a two-tailed test. And so we would have it set up here as tail type as two-tailed. Our alpha level next is that level of probability that we want to test our hypothesis. So what we're saying here with this alpha level of 0.05 is that there will be less than a 5% chance we're going to make a hypothesis testing error if we decide that the difference we're seeing is statistically significant. And so this is a pretty standard alpha level that we want to test hypotheses at. If we wanted to be even more sure we weren't making a type 1 error, we could test at the 0.01 level or the 0.001 level. And again, that's going to vary depending on the kind of analysis you're doing, but we're doing a pretty low stakes basic analysis. So we're going to leave our alpha level at 0.05. The rest of this can stay as is, and we'll talk about what the Shapiro-Wilk test will help us do in a couple minutes. But once we've selected these options, we can go ahead and click Save Options. Now the next thing we need to do is select the dependent variable or the sample of scores that we want to compare to the population. So we click on this Add Modify button and we go to this drop-down menu and we want to select reading 1 as our outcome that we want to look at, our dependent variable that we want to look at. So we've chosen reading 1. It's a scale variable, which means it's numeric. And we go ahead and click Confirm. Now the next thing we need to do is just below that is indicate the test value. And what this is the population mean that we'll know or will be given that we then want to compare to our sample mean. So we click Add Modify and we enter in that population mean. So in this case, let's say the population mean is 81. Okay? And that's all you have to enter in is that value, whatever it may be. When we do an exam or we do examples of this kind of test, that value will be given to you. You'll know the population value, so you'll be able to easily enter this in. Okay, once you've entered that value in, you go ahead and click Confirm. And now we can see we've got our dependent variable entered. We have our test value or our hypothesis, our null hypothesis, our population mean entered in. And now we can go ahead and click Calculate. And so what I want to do first is go to the raw output because we're going to have to get used to viewing raw output so we can interpret some of these things. We want to get good at looking at the raw output ourselves and not just rely on what Intellectus provides in the narrative output. So there's a couple things we want to look at first. So we can see the bottom here is the raw output for what we just did. So here's our variables, reading number 1. Here's the sample size, 150 people. Now the first thing we want to look at is the Shapiro-Wilk test. Now what this will tell us is if the data in our reading number 1 variable is normally distributed. Okay? So if this p-value right here is greater than 0.01, then we know we have a normally distributed set of data. So as you can see here, this p-value is 0.63, that is greater than 0.01. So this is a way for us to double check ourselves. We know then that our data is normally distributed. So we've met the assumption for doing a one sample z-test. We can also check this, as we mentioned before, by looking at the skewness score of that data. So the Shapiro-Wilk test is just another way of assessing the normality of data that we might be working with. Okay, we have that, so we're in good shape. We know we've done an appropriate test here as far as meeting the assumption. We can then look at the value for the mean of our sample, which is the reading number 1. So the students in our class scored on average 84 on the standardized test and with a standard deviation of 7.3. The next thing we look at is the actual z statistic. So that is the standardized score that's been produced for us in the formula that will give us an idea of how far away the mean of our sample is from the mean of the population. So Z represents, as we've learned in your reading and some of the videos we've watched, is a standardized score. It tells us the distance that a score is from the mean of a population, in this case 81. So we know that about 5 standard deviations away from the mean of the population is the mean of our sample. So that is a large distance away from the population mean. And if we look at our p-value here, what we'll often see is if the p-value is really, really small, we'll see the p-value actually denoted in scientific notation. So what this is saying here is we see this e minus 0.07 is there are actually 7 zeros in front of this 2.2. So that means that the p-value is actually 0.00000002. So that's well below 0.05. So we're able to then reject the null hypothesis and state that the mean of our sample is statistically significant in its difference with the mean of the population. So as we've again learned in our readings, when the p-value we calculate is less than the p-value we've established for our null hypothesis, then we can reject that null hypothesis. And so in this case, we can say that our sample is significantly different from the population based upon the reading score. And so we can, report the mean of the sample, report the mean of the population, and demonstrate that that difference is statistically significant. It is very unlikely that the difference is just due to chance, that there's something that we can't really explain the difference that's there, but it's just there. In this case, we can say with very good confidence that this difference of 84 and 81 that we're seeing between our two means is not just a chance occurrence. There's something that explains that difference. And presumably it's how good a job we've done teaching reading to our sample. And so their score on the standardized exam is that much better than the rest of the population. So in summary, what we've done here is we've learned how to do a one sample z-test in which we're testing a null hypothesis between a sample mean, a set of sample scores, compared to a population mean. And in this case, we've been able to demonstrate that our sample mean is significantly different than our population mean. So hopefully you've been able to learn how to do the basics of a one sample z-test from this video. And we'll be getting into much more detail later of, again, how to continue to apply this technique. But now you at least know how to do the actual analysis technique within Intellectus.